So let's go ahead and look at another problem from section 8.2. Okay, this is problem number 4. And it says that a mean biologist claims that the mean length of mature female pink sea perch is different in fall and winter. Okay, so in other words, we're comparing the mean length of all mature female pink sea perches in fall and in winter. Okay, and you might have to look up what a sea perch is. I'm not quite sure, but look that up if you want to know what it is. But let's continue. A sample of 6 mature female pink sea perch collected in the fall has a mean length of 113 millimeters and a standard deviation of 13 millimeters. Okay. Then a sample of 8 mature female pink sea perch collected in winter has a mean length of 104 millimeters and a standard deviation of 9 millimeters. Right, so obviously the sample means are different, right? So the sample mean for fall was 113, while the sample mean for winter is 104, right? So clearly the sample means are different. Okay, but remember the samples, if they're representative of the entire population of female pink sea perches, right, the samples should both be representative of their respective populations. Okay, so we're going to use the information from the samples to determine, okay, if there's a difference between the mean length of female pink sea perches in fall and in winter. Okay, so in other words, it's not enough to say that because the sample means are different, it necessarily means that the population means are also different. Okay, so that's why we're going to do the hypothesis test. Okay, so it says at a significance level of alpha equal to 0.20, can you support the marine biologist's claim? And then it says assume the population variances are equal. Okay, and then assume that the samples are random and independent, and then the populations are normally distributed. And we're going to complete parts A through E below. Okay, so in part A, we're going to identify the claim and state the null and alternative hypotheses. So what is the correct claim? Okay, so carefully read the answer choices. Okay, the only one that makes sense is answer choice A. Okay, so again, this is the claim. The mean length of all mature female sea perch in fall is different than the mean length of all mature female sea perch in winter. Okay. Since we're dealing with 2 different means, okay, from 2 different populations, right? The mean of the first population is the length of all female sea perch in the fall, and then U2 would be the mean length of all female sea perch in winter. Okay, so the null hypothesis will be that there's no difference between the mean lengths of the sea perch in the fall and winter. So mu1 minus mu2 is equal to 0, and the null hypothesis. All right, and then the difference between the 2 means, okay, is not equal to 0 in the alternative. Okay. So remember, it says in the claim that these 2 means are different. Okay, so different means not equal to. Okay, it doesn't necessarily mean less than, it doesn't necessarily mean greater than, right? Different means not equal to. Okay, so you put the not equal to symbol in the alternative hypothesis because we use the not equal to symbol in the alternative. All right, that means you put the opposite. So the opposite of not equal to is equal to. So that's what we put equal to in the null. Okay, so the null hypothesis is that the 2 means are equal, and then the alternative is that the 2 means are different, or not equal to each other. Okay, then the question is, right, which hypothesis represents the claim? All right, so it's clearly the alternative hypothesis in this case. So this is the given claim in our problem. Okay, right, because it has the word different. Right, if it had the word equal, right, if it had the word the same or they're equal, right, then the claim would be the null hypothesis. Okay, this also means that since this is a not equal to symbol, right, this is also a two-tailed test. Okay. So as you'll see in a minute in this problem, right, when we go through and do the hypothesis test, it's going to ask us to get the critical values of the test. Okay, so we just said the alternative hypothesis is the claim. Okay, now we're going to go through and find the critical values. Remember, the critical values of this test are based on the significance level of the test. Okay, so we're going to go ahead and go to StatCrunch. Okay, so now we're going to go ahead and use StatCrunch to determine the critical values of this test. Okay, and the critical values are based on the significance level, which is 0.20. Okay, so in StatCrunch, we're going to go to Calculators from the Stat menu and then click on the T-distribution calculator. Because this is a two-tailed test, we're going to select the between option. Now, depending on whether the problem says about the standard deviations, right? Whether we assume the standard deviations are different, or we assume that the standard deviations are the same. Okay, that's going to determine the degrees of freedom for the problem. So that's an important distinction. Okay. So normally, right, if we know nothing about the standard deviations, right, the degrees of freedom would be the smaller sample size minus 1. Okay, but if you go back and read the problem carefully, right, it says at the end, right, we're going to assume that the population variances, okay, are equal. Now remember, right, that the square root of the variance is a standard deviation. So if the variances are equal for the two populations, okay, then that automatically implies that the standard deviations are also equal. Okay, so if you go to the book, all right, there's two different ways to calculate the degrees of freedom. Okay, now if we assume nothing about the variances, right, the variances are not equal, right, then this says that you take the smaller sample size and then subtract 1 from it to get the degrees of freedom, right? That's basically what this is saying, right? And that's what we did in problem 2. Okay, but because the problem says that the variances or standard deviations are equal in the two populations, okay, then our degrees of freedom is equal to the sample size of the first sample plus the sample size of the second sample minus 2. Okay, so quickly going back to the problem, right, we see that the first sample had 6 of these female sea perches, okay, and the other sample had 8. All right, so when we do 6 plus 8 and subtract 2, like it says in the book, right, for equal variances, okay, our degrees of freedom is 12. Okay, so that's what's going to go here in this box, 12. All right, and we're going to type in 1 minus 0.20. So 1 minus the significance level is going to go in this box here. Okay, it's always 1 minus the significance level. Okay, so the critical values are the same value because the t-distribution is symmetric, but one's negative, one's positive. So rounded to 3 decimal places, right, the two critical values are negative 1.356 and positive 1.356. Okay, and they can put them in any order as long as you separate them with a comma. All right, guys, so we got the correct critical values. So just like the other problem, since this is a two-tailed test, okay, it's going to be this option, right? The rejection region, okay, the rejection regions are going to be to the left of the negative critical value, all right, and then to the right of the other critical value, to the right of the positive critical value. Okay, next it's going to ask you to find the standardized test statistic. Okay, so this is where you're going to take the information from the problem and enter into StatCrunch. Okay, so we're going to go to T-stats, two-sample. Okay, so the tests we do in this section are called two-sample t-tests. Okay, since we're dealing with two samples and we're comparing the two means from the populations. Okay, so two-sample t-test. And we have a summary of the data rather than the actual data. All right, I'm going to enter the information off camera. Okay, so I went ahead and entered the sample mean, sample standard deviation, and sample size for both samples. So next we're going to set up the null and alternative hypothesis as we have set them up for this problem. Unfortunately, if there's another symbol used here in the null hypothesis, we won't be able to change it. So in StackCrunch, by default, the symbol used in the null hypothesis will always be equal to. Okay, so we can't change that. Okay, but it doesn't affect how we do the problem. Okay, and then in the alternative hypothesis, right, we have the not equal to symbol, right? So we're assuming that the two means are different. Okay, so before we continue, I haven't talked about this option here, right, where it says to pool the variances. Okay, so because in the problem it says that the variances from the two populations are equal. Okay, if you go to the book, it says something about that if the population variances are equal, right, then the information from the two samples is combined to calculate a pooled estimate of the standard deviation. Okay, which is used by this symbol, which is given by this formula, which we won't use. Okay, so that, in other words, if the variances are assumed to be equal, okay, you account for that in StackCrunch by selecting this box. Okay, that's only when the variances are equal, right? If you forget to check this box, you're going to get an incorrect result for the test statistic. Okay, so again, when the variances are assumed to be equal, okay, make sure you check pool the variances. Okay, so once you've entered everything correctly, we can also create optional tables and graphs. Okay, for example, you can create an optional p-value plot. Okay, but then that's not necessary. Let's go ahead and get our results. Okay, what we're looking for is the test statistic. Okay, we're going to go ahead and round that to 3 decimal places. So the test statistic to 3 decimal places is 1.536. Okay, so I believe I did everything correctly. Let me just go and double check that. Okay, so the t-stat was 1.536. Okay, I must have entered it incorrectly. So 1.536. Okay. All right, so once we have that, we compare that with our critical values. Okay, 1.536. So if it's either less than the negative critical value or greater than the right critical value, it would fall in the rejection region. If not, it doesn't fall in the rejection region. So remember, our two critical values were negative 1.356 and positive 1.356. Okay, so it might be difficult to do without some sort of graph, but let's talk our way through this. So 1.536. Okay, it's obviously greater than this one. Okay, but is it greater than this one, the positive critical value? And the answer is yes. So 1.35 is our critical value. Okay, and then 1.53 is the test statistic. Okay, which is clearly greater than the larger critical value, which puts it in the rejection region. Okay, so in this case, we reject the null hypothesis. Okay, and then for the conclusion at this 20% level of significance, so in other words, we're going to interpret the decision in the context of the claim. So at this level of significance, right, we have support for the alternative hypothesis, so we would select there is enough evidence to support the claim that the mean lengths of these female pink sea perch are different in the fall and winter. Now, if we had not rejected the null hypothesis, right, then we would select this option. There is not enough evidence. Okay, so we've correctly completed problem 4 from the homework. Okay, so before we conclude the video, this is a two-tailed test, so the rejection regions in both tails. These are the critical values, which are the cutoff values for test statistics that fall in the rejection region. So clearly our test statistic of 1.536 is in the right tail. It's greater than 1.536, which means we reject the null hypothesis, and then this would be our conclusion.